All right. So I'm going to show a demo for how the audio transcriber project works. So the first thing you got to know is that when you use Discord, you can use a tool called Craig, and I think you can do like join, and when you do, it starts recording whatever's going on in a channel. But let's assume that you've already recorded your audio and you've done that. You'll get a folder that looks like an Audacity project, and inside of it you'll get a whole bunch of these FLAC files, and those FLAC files are the ones that we're going to be really processing. So if I were to like open any one of them up, let's say just like move one here, I'll just sort of play a few seconds of audio just so you guys get a sense of like what it looks like. Getting it to play
Stuff. I got +3 on the stuff.
There you go. For example, that's what it looks like. But you can see that in the sound file, there's a bunch of these empty silences because those are like where other speakers are talking usually. Okay, so you have these files, and we're gonna use these files to create transcript. So this is the project itself. Like it pretty much is. You have like your inputs and your outputs folder. And prompts, and mostly your source, and pretty much the way that like before we run this program, I'll just sort of spend a couple seconds talking about the high level architecture. Like this is like a modular data processing audio pipeline. So there's inputs and outputs, and each stage of this program is designed to be independent. So it'll like read inputs, do some processing, and then write its outputs to this like shared outputs folder for a given step. And the next stage can reference any previous step's output as its input. So that's good and all, but I think like in order to make it feel like a program instead of like a collection of scripts that do random things, we needed to add a few things on top. The first is like a lightweight state management system, so you just know like when a given stage was last run and how long it took, and we do this through this like stats JSON. That's helpful because if you like run a program and it errors out, you could rerun a program from whatever the last known state was. And then the second is really just like a CLI that can wire a lot of these things together. Oops, and so, wiring this so that you could, in the default, just run the full pipeline, but then you can do a lot of things like you can run specific stages if you like set those options, or you can like clean the workspace and do all this sort of stuff. And so, those two things sort of help make this a real program. The benefits of this architecture is that like I can rerun any of these steps in an idempotent fashion, in like inspect or modify, and so being able to run any part of the pipeline independently means that I could do a lot of quality evaluations or iterative improvements on specific stages. It's also a lot faster of a feedback loop. So it makes it easy. It makes it easy for us to improve the program. Also, this structure of like independent modules makes it really easy to just add new steps at any part of the pipeline if I want to do additional things. So I kind of designed it for that use case. But so what we'll do is we'll just start running some of these programs. I'm already in a Vend, so I'll just do like, so I use UV. And so, the first thing is just running status, and it lets me know like, okay, I've run this pipeline before. I could do like UV run transcribe, run help, and it'll tell me like, hey, I can add a stage, and I can just run any sort of set of stages, or I could just like start from a specific point and complete. I could, reset the whole thing, so I start over again, and if I do like, there you go. So like, there you go. If I were to run the program, it'll just start from scratch, and I can just do like clean. It'll prompt me. Sometimes it does this, so I have to do like fix my shell, and so I'll like clean out all the inputs, And so now what you can see is I have no inputs, I have no outputs, I have no status. Everything has been wiped. So now we're actually going to run this whole thing. That's kind of a quick view of how the command line works. But let's say I take these files and move them over to the inputs folder. That's all I need to do to really get started. So I'll just do uv run, transcribe, run. Cool. All right, and so this is actually the program running, so I'll walk through the steps. So the first step was just the bootstrapping, and this just checks like, do we have all the necessary system dependencies? Do we have ffmpeg installed? Do we have, can we download the ML models and the LLMs necessary to run this program? If not, it'll download it here, so it's cached for later steps. It'll check to see if you have the OpenAI API key. Cool. And so once it's like, okay, cool, you can actually run this program on your computer, then it actually starts. The first step is just converting those audio files from FLAC to 16 kilohertz WAV files using FFmpeg. And most ML models do better on that specific audio format since it's the one that's most available in the training data. So we do this step in parallel using subprocessing. So this is just happening simultaneously. Then we're into the next step, which is voice activity detection, or VAD, and we use Silero because that's the best in class and it's free and open source. So, by the way, Silero can be used for real-time voice detection, so this is going to be good if you want to have like interactive agents. And when Silero is done, so you can see now we have this outputs folder, we have the WAV files now, and if we go to Silero timestamps, it's still processing, but what we should expect to see is a bunch of these timestamps being created. And so why do we do VAD to begin with? One, the whisper step, which is starting to run right now, is the longest step in the pipeline. It's going to take a decent amount of time. So getting voice activity detection, getting these timestamps of when a speaker is saying something allows you to like cut out all the spaces of dead space. And that happens a lot in a multi-turn conversation. The second and big reason here is that Whisper will hallucinate like crazy if you give it a bunch of silence and ask it to transcribe that silence. It'll just like regurgitate a nonsensical phrase for like thousands of lines, and that actually breaks a lot of things. So you really do need VAD in order to make sure that you can get any quality of transcript out. So we're running the Whisper pipeline now. This step takes about 10 minutes, but when I first started this program, it took about 2.5 hours. I spent a lot of time sort of evaluating and benchmarking different implementations of Whisper. And so there's actually like another repo I created called Whisper Bench that sort of captures the results of that. But I ended up running into like the MLX community on Hugging Face, and MLX is like Apple's framework for optimizing any language model to work on the Apple neural engine. MLX is their framework. So the MLX community on Hugging Face allows you to take pretty much any state-of-the-art model or just a ton of the most valuable like LLM or ML models and get it to work on a M1 based laptop really well. So this allows you to sort of play with this stuff locally. This part's kind of boring, so I'm just gonna like speed through this. I'll probably like fast forward and then I'll probably just start talking again when this is done running. All right, so this step is about to finish. I just want to just show you guys like this step runs in sequentially just because this takes like 22 gigs to run locally. And so, but you know, transcription that probably took, you know, again, 9 minutes 30 seconds is not bad at all, so it's because it took a long time before. The final step here is probably the least interesting, but you know, after you have individual transcripts for each person, right, that like is their voice lines, you need to actually merge this together. So the last step is just like a GPT cleanup pass, and we sort of farm out the we first merge the transcript, and then we like find adjacent chunks by the same speaker and merge those together. And so when we feel like we have like a singular transcript, then we just kind of do one final pass with it with ChatGPT, where we just try to make sure that we fix proper nouns and correct the conversation so that it flows more smoothly without actually changing what people are saying. And one of the things to be careful of is if you do have hallucinations that came from the whisper output, if you try to feed that to ChatGPT, you'll actually cause a context overload issue, just like a Stack Overflow or something. And so you end up needing to remove that before you pass it to ChatGPT. Otherwise, it'll just like start dropping lines once it does a revamp. But the final step, of course, is just passing it, cleaning it up, and it'll then spit it out into a final output here, which is GPT cleanup. It's not done yet, but we do this again. We do this step in parallel. And this step used to take about 40 minutes when you try to sequentially process it, but now it takes about like a minute and a half, 2 minutes to process all of that. And so you can sort of see this is what the outputs are at each stage, and if I had any issues with any one file, I could dive into the code base, fix it, and then rerun that step. There you go. It's just processing, and I think we're done. Great. And so if I do UV run transcribe status, you should see, hey, this is the last run, this is how long it took, and overall it took about, I don't know, 15 minutes, less than 15 minutes. So that's the program. Hope you enjoy.